Welcome to our lesson on solving systems of equations in three variables. Our learning targets for this lesson are to be able to solve any system of equations with three variables, and then to use that to solve some real-world problems. So we're going to have three different scenarios or three possible outcomes or possible solutions with these systems of equations with three variables. And I need to talk to you a little bit about what an equation looks like that has three variables, an x, y, and we're adding a z variable. So we haven't talked at this point a lot about three space or three-dimensional geometry. And so when we have three dimensions, we have a variety of different outcomes here. So the three different outcomes that you could have one solution where all three planes intersect at a single point. And when we have three variables, each of these equations represents a plane rather than a line. We're used to an x and a y variable, and those form lines. When we add that third variable, it forms a whole plane. And remember, a plane from geometry goes on in each direction infinitely. It goes on forever. So one of the solutions then is if all three planes intersect at a single point, we get a single point as a solution. So that's one possibility. Now we can also have a possibility where all three planes intersect, but their intersection forms a line, which you see in blue here. And so there's an infinite number of solutions there. There are a lot of x, y, and z coordinates on that line. So that's what it looks like graphically if we have infinitely many solutions. And it's also possible that we may get no solution. We could have three planes that are parallel and don't touch. We could have two that are parallel, but one plane that intersects the other two. So the three planes have nothing in common. And likewise on the left side here, these three planes all intersect, but only two at a time. So there's no solution together where all three planes share any single point. So let's go ahead and look at some examples and look at the algebra and interpret what it means here and figure out how we solve these systems. So I have three equations here. We have to have the same number of equations as unknowns, or else we can't solve the system. Since we have three variables, we need at least three equations. And so we have three variables, three equations. And so the first thing we're going to do is to try to eliminate one of our variables. Okay, so we're going to try to get this downsized to two equations with two unknowns. And the way we're going to do that is to pick any two equations. I picked equation 2 and 3 because the x variable has the same coefficient. And I multiplied equation 3 by -1 to change the signs. And I'm going to add these together. So equation 2 I just rewrote. Equation 3 I multiplied by -1, which just changes all the signs. And then I went ahead and added those. You can see the x variables drop. I get 2y's plus 8z's equal to -32. So we have one equation now with two variables. And I used equation 2 and 3. Well, if I use equation 1 and 2 and get the x variable to drop out, then I'll have a second equation with the same two unknowns, with y and z, the same variables. So I went ahead and I multiplied equation 1 by -2, because then when I add these two equations together, my x variable will drop out. Since this coefficient is 2 and I want the opposite sign, I multiplied the whole thing by -2. So every one of these coefficients is multiplied by -2, giving me this new equation 1 right here. So that's where that came from. And equation 2 I just rewrote, so no changes there. Then I added these together, and I get -5y plus 1z equals -25. So now what I'm going to do is I'm going to combine these two equations. Equation 4 and equation 5 is what I call them. They're both in terms of y and z. And this is just basically starting from what you know from our last couple of sections where we have two equations and two unknowns, a system of equations that we're trying to solve. And we're using elimination. You could use substitution, you could use graphing, but I think for the most efficient way to solve these is to go ahead and use elimination. Well, if you look at these, what would be the easiest way? I could try to get rid of the y variable, multiplying the top one by 5 and the second one by 2. Or I could multiply this second equation by -8 and get the z variable to drop out. That seems like it would be the most efficient, so that's what I did. I rewrote equation 4. I multiplied equation 5 by -8. So -8 times each of these terms gives me this equation right here. The z variables drop out, as you can see. I get 42y is equal to 168 when you take 200 and subtract 32. Dividing both sides by 42, I get y is equal to 4. Well, now that I know what y is equal to, I can substitute that into either of these two equations, any of these two equations with just y and z. And so I picked equation 4 just because the numbers are smaller, and I substituted in 4 for the variable y, which allowed me to solve for z. So I had 8 plus 8z is -32. Subtracting 8 from both sides, I get 8z is -40, and then dividing by 8, I get z is -5. Okay, so now I have y and z, I only need x. Well, to figure out what x is, I can plug y and z into any of my original equations in the beginning here and figure out what x is. So I went ahead and chose equation 1, I believe is what I chose. And so here's equation 1, I just rewrote it, and I substituted in the variable 4 for y and -5 for z. So I get an 8 minus 5, which is 3. And if I subtract 3 on both sides, I get x equals 7. So I ended up with a specific point, the point 7, 4, -5. Remember, these have to go in order. Your x variable, then your y variable, then your z variable. So this tells me that these three planes, the equations represented by these three variables, these three planes, intersect at a single point. Let's try this example. Solving this system of equations, our first goal is to eliminate a variable. So when you're looking at these, if I just look at equation 1 and equation 2, let's just take the x variable. What can I multiply by? If I want to get these coefficients to drop, I could do this one by 6 and this one -4, but I can actually multiply by smaller numbers. The least common multiple would probably be 12. So I'm going to multiply the top one by 3 and the second one by -2. So if you have questions on why I chose that, ask me in class. It's basically a random thing. You can pick which variable you want to drop out, and that's your goal. So if I multiply the first one by 3, I have that here for you. Second one by -2, so it changes all the signs, and then multiply the coefficients by 2, and then add these together. Well, when I add them together, you'll notice every single one of those variables drops out, but the right-hand side also drops out. I get 0 equal to 0. That's a true statement. Now, since that's a true statement, I know I'm going to have an infinite number of solutions. But the one thing I need to check is, how does that work with the third equation? So I need to check to see if that plane that is represented by these two equations, those represent the exact same plane, does that intersect this third plane? So that's what I'm going to check next. So I'm going to take equation 2, and I multiplied it by -5. I'm going to try to get my z variable to drop out this time. Multiplied by -5. Equation 3, I multiplied by 3. So I'm trying to get a 30z in both of these. So multiplying by -5, I get -30x minus 45y minus 30z is -90. Multiplying all of the coefficients in equation 3 by 3, I get 15x minus 24y plus 30z equals 60. And again, we're going to add these together. And when I add them together, I get another equation. So I do get the z variable to drop out, but I get an equation. Now this equation represents a line. Since the result is the equation of a line, we know that there are an infinite number of solutions. Okay, so that's going to be a scenario like I showed you in the first slide, where we have an infinite number of solutions because they intersect to form a line. And lastly, this example, solve this system of equations. Again, we're going to eliminate a variable. And let's see, I think in this one I chose to eliminate the variable a. So I multiplied the first one by 3 and the second one by -2. So I'm multiplying the first equation by 3, second equation by -2 to get my a variables to drop out. But this time you'll notice when I do that, again, all my variables drop out and I get a 0 on the left. But on the right-hand side, I don't get a 0, which gives me a false statement. So once that happens, we don't have to go any further. That's a no solution. So those are examples of all three of our scenarios from our very first slide, where we have either one solution with three, an x, y, and a z variable, an infinite number of solutions where they intersect in a line, or no solution where they have nothing at all in common in those three planes. That will do it for this video. We'll see you next time.